Well, first of all, I would like to thank you all for joining. My name is Filip Lemic, and the title of my today's talk is Intelligent Reflective Surface versus Mobile Relay Supported Non-Line of Sight Avoidance in Indoor Millimeter Wave Networks. And what I would like to mention is that this is the work of my alumni student, Maria. Kudos to her. So let me start by introducing this work. I think we're all aware that 5G is here and 6G technologies are at the moment being rapidly explored and developed. And one of the primary general goal of each new generation of wireless communication technologies is faster and more reliable communication. For those reasons, the 5 and 6G are starting to look into millimeter wave and above frequencies. The benefit of going into high frequencies is the large availability of bandwidth, which allows for high data rate and data rates, lower latency, and more reliable communication. But also there are some drawbacks, and the major ones in the context of this work are the high free space path loss and sensitivity to obstacles, sensitivity to blockages. For this reason, for the high free space path loss, the communication and millimeter wave and above frequencies is usually focused in a way that the energy of a beam is focused in the direction where we want to communicate. So one example in which such technology is providing high data rates and reliable communication will be useful is full immersive multi-user VR setup. And this is depicted in the figure on this slide. As we can see, there is a number of full immersive VR users, and by full immersive, we mean that they feature 6 degrees of freedom in terms of their mobility, so they can rotate their head, but they can also walk and move around the environment. Their virtual reality content is delivered to them using millimeter wave and above frequencies. So it's kind of intuitive that in this setup, there is a possibility that one user will essentially act as an obstacle and destroy the connectivity for the other users. And there are technologies that can be used for mitigating this negative effect of non-line of sight connectivity or broken line of sight connectivity. And one technology that is kind of emerging rapidly is intelligent reflective surface. And this technology has been used for non-line of sight avoidance in scenarios such as Industry 4.0 as depicted here, but also in the data centers as depicted here. So this is the intelligent reflective surface as depicted here in the slide is one of the technologies that we consider for non-line of sight avoidance in the above before discussed scenario. Another technology that is perhaps a bit less discussed in the context of non-line of sight avoidance, but is discussed a lot in the context of full immersive virtual reality setups is mobile relay. And these mobile relays can be implemented as small unmanned aerial vehicles. So as you can see here, this is one implementation of such vehicle. And this drone, this small drone, is providing tactile feedback to the VR users. You can see another example set up here in which quadcopter is envisioned to also be providing some kind of feedback to the VR users. So obviously, the mobile relays will be available in the setup that we are considering, that they potentially can also be used for non-line of sight avoidance in such setups. So the goal of this work is to establish which technology provides higher signal-to-noise ratio in average of communication in non-line of sight conditions, so with a broken line of sight. So we model the SNR of such non-line of sight communication as depicted on the slide. So in terms of the intelligent reflective surfaces, so the transmission from the source towards the intelligent reflective surface and forward toward the destination is modeled with the equation given at the top of the slide. This equation depends on the transmit power by the source, on the noise floor, on the number of antenna elements that the intelligent reflective surface features, and on the size of the intelligent reflective surface. It also depends on the location of the source, destination, and the intelligent reflective surface in the environment. In terms of the mobile relay, so the signal-to-noise ratio can be modeled as the minimum as the smaller signal-to-noise ratio of the two components. So the first component is the transmission from the source towards the mobile relay, which is kind of modeled here. And then the next one is the transmission from the mobile relay towards the destination. And similar to the left-hand side here, the SNR depends on the transmit power, on the noise floor, on the number of antenna elements featured at the mobile relay level, and on the location of the devices participating in communication. So in our system analysis, we utilize a grid search. So we exhaustively search all possible locations of the intelligent reflective surface and the mobile relay so that we find the optimal positioning of the intelligent reflective surface and the mobile relay for the given location of the source and destination. In our analysis, we assume that there are different degrees of freedom in terms of the positioning of the intelligent reflective surface and the mobile relay. In particular, we assume that the intelligent reflective surface can be deployed, mounted on the outside walls of the environment of interest as depicted on the left-hand side in the slide. In terms of the mobile relay, we assume that the mobile relays feature higher levels of freedom in terms of their positioning, so they can take any position in the environment of interest as depicted on the right-hand side in the slide. And the overall goal is the SNR maximization. So maximization of the SNR of the communication link between the source and the destination. So this slide depicts one example of how this grid search is performed. So you can see on the left-hand side how we change the potential location of the intelligent reflective surfaces along all walls of the environment of interest. And in this particular example, the SNR is maximized if the intelligent reflective surface is positioned on the right-hand side, on the right-hand side wall in the environment, and this SNR equals roughly 10 dB. In terms of the mobile relay, the first thing to observe is that there is much more potential locations where we can position the mobile relay. That's number one. Number two, it's to observe that at some locations, we set the SNR of the mobile relay to -10 dB, and this is in case the SNR of the non-line of the SNR of the communication, assuming non-line of sight, is higher than the SNR of the communication in the line of sight. We assume this scenario to be infeasible. And as we can see, in this case, the maximized SNR is roughly 40 dB. So these are the kind of the results, the comparison of the SNRs achieved by the utilization of the intelligent reflective surface and mobile relay for non-line of sight avoidance in the considered scenario. So first of all, we consider three different sizes of the environment of interest, and these are kind of some practical sizes that we believe they're going to be utilized in such full immersive virtual reality setups. And then we consider on the x-axis a different number of antenna elements at both intelligent reflective surface and mobile relay level. And then the y-axis provides the SNR. So the first thing we can see is that as we increase the number of antenna elements for both technologies, the SNR increases, which is kind of an expected behavior, and it kind of enhances the reliability of our less intuitive findings. We can also see that as we increase the sizes of the environment of interest, the SNR generally drops, and the reason for that is that the communication ranges increase, and that affects the average SNR observed on the links. And then the final conclusion is that mobile relay essentially features significantly higher average SNR of communication. And the main reason and direct reason for that comes from the fact that there is more degrees of freedom of the positioning of the mobile relay. So it can take more optimal position for relaying. And a set of conclusions. So in this work, we have considered intelligent reflective surfaces and mobile relays as potential technologies for mitigating the negative effects of non-line of sight connectivity in indoor millimeter wave networks, which we believe are going to be used in full immersive virtual reality setups. So for the considered full immersive virtual reality setup, mobile relays achieve significantly higher average signal-to-noise ratio of communication compared to the intelligent reflective surfaces, and this is a direct consequence of having higher degree of freedom in their positioning. On the other hand, Intelligent reflective surfaces have intrinsic advantages that could make them preferable to the relays, such as their low cost, higher energy efficiency. So as part of our future work, we plan to derive a comparison framework. And in this comparison framework, we hope to be able to capture different performance metrics, including production maintenance costs, energy consumption, reliability, and latency. In addition, our future aims are faster optimization approach for intelligent reflective surfaces and mobile relay positioning, so faster than the exhaustive search. Consideration for three-dimensional environments. Well, in this work, we have considered two-dimensional positioning of the mobile relay and intelligent reflective surfaces. And we will also account for the scenarios with multiple users. And we will also account for the delay in the positioning of the mobile relay. Well, in this work, we have assumed that the relay can position itself at the optimal location instantaneously. And this is it. I would like to thank you all for joining. And if you have some questions, now is the time.